Hi, this is Dr. Y.S. Rao, Dean Academics and R&D from Sardar Patel Institute of Technology, Director Go Green Technologies. This session I have created for the purpose of doing some laboratory experiments for the subject computer architecture and organization. Though we are using the latest generation computers or laptops, the CPU could be i3, i5, i7, i9. But when it comes to the subject computer architecture and organization, we would like to know how this is evolved over a period of time, the computer architecture and organization. When it comes to architecture, we all know that most of the countries and industry till today is using X86 computers. That means Intel architecture based computers. We understand no mobile is using, no other systems is using X86 architecture when it comes to embedded systems, when it comes to IoT devices. We don't use X86 architecture. However, when it comes to computer desktops, popularly we use 8086 architecture even till date. So it is always upward compatible. So that's the reason we need to understand what is microprocessor, what are the generations of the microprocessors, particularly Intel. But today the CPU we don't get x86, but however if you want to practice the root level some of the commands, then we still would like to practice those 1970s 80s instruction set, operating system, or some of the tools. So this is a big problem. So how to solve this problem? So this topic is all about how to write the programs in assembly language of 8086, and those programs we would like to execute using the latest computers. Though 8086 physically not available but logically available. Similarly, the 1980s operating system, which is a DOS operating system, physically not available but virtually it is available. So we will be executing all these programs, x86 assembly language program, in a virtual environment by using the latest generation computers. So that is the topic where I will be explaining as well as demonstrating. To begin with, what is x86 and how these generations are evolved, like particularly in terms of memory management, like what is called real mode, protected mode, virtual mode. Then we will discuss about the operating system like disk operating system and some of the tools which are available in disk operating system. Interestingly, when we study about any microprocessor, whatever is the number of address lines it is having, we say that is the addressing capacity. So the number of address lines always determines the depth of the memory, and the number of data lines always determines the width of the memory. Let's say, for example, if you look at first CPU, first popular CPU, though it was not used in computer, but still being a 8-bit CPU, 8085 is having 16 address lines. So since it has 16 pins physically available on the chip, the addressing capacity is 2 to the power of 16, 64 kilobytes. I said bytes because the data width is 8-bit. So 64 kilobytes is the addressing capacity of 8085. Then it comes to next generation, the popular CPU 8086, which was mainly used in computers called personal computers. In 8086, they have increased the number of address lines to 20 address lines. So physically 20 pins are available on the IC, address lines A0 to A19. So 2 to the power of 20 is 1 megabytes is the addressing capacity. However, the data lines are 16, but in order to maintain the compatibility of byte addressing capacity, they still maintain 1 megabytes of addressing capacity, or you can say 512 kilo words of addressing capacity in 8086. The next generation is 8088, because 8086 is having 16 physically data lines, but the industry was not ready to accept 16 external data lines. They want 16 data lines internally inside the chip, but not externally. So they have provided, the reason why they have not accepted is all the peripherals which are available, like keyboard controller or the display controller, hard disk controller, floppy disk controller, serial ports, parallel ports, all of them are timers, interrupt controller, DMA controller, all of them are 8-bit. So industry doesn't want to shift it to 16-bit external data bus. So Intel has released the degraded version of 8086 called 8088, which is having same number of address lines. However, the number of data lines are, they have made it 8 externally. Internally it is 16. So it is compatible to all the peripheral chips like 8255, 8251, 8237, 8254, all those peripheral chips. So that is the popular addressing capacity, what is called real mode. Real mode means 8086 mode, which is having 20 address lines. The addressing capacity is 1 megabytes. Then 186 came, 286 came, 386 came, and so on. Then lot of changes are made, particularly in terms of memory management and the protection mechanism. Because after 8086, Intel wants the computer to be made as a multi-user, multitasking system, like a workstation. So when you are providing multi-user, multitasking, the first question arises is the protection. How do you protect the memory between the tasks and between the users? So protection has to be provided at the CPU level itself. So they have provided a protection mechanism. Along with the protection mechanism, they also provided, virtual mechanism. Virtual means not real, as the name says. So the memory management unit itself is having 3 ways of addressing the memory. One is called real addressing, second called protected addressing, third is called virtual addressing. Now it is an interesting, if you take a case study of 386, 386 is having 32 address lines, physical lines, actual 32 pins are there physically. That means 2 to the power of 32, it can address 4 gigabytes of physical memory. However, like I said, the memory management unit has the capacity to address 2 to the power of 46 address lines, that is 64 terabytes of memory it can address, though physically those many pins, those many address lines are not available. that is called virtual. So where this memory will come from, though it's not physically available, it is coming from the hard disk. So secondary memory. So using the hard disk space and exchanging the program and data from the hard disk to the physical memory is called virtual memory. So that is why they had increased the number of addressing capacity to the 46, 64 terabytes. Otherwise, even today, none of the computers have physically 64 terabytes, right? Even 8 GB is more than enough. But even then, in 1980s itself, you can say 90s itself, they have made 64 terabytes of virtual memory. And then what is protection? Like I said, protection means memory protection between the users, between the tasks. When you are having a memory reserved for a specific user, specific task, then you need to protect it. The memory is also different types, different purposes, like program, data, stack. When you are having different purposes, then it need to be protected between the users. So how do you protect the memory is what we will discuss quickly in this session. Though the purpose of this session Alright, so if you see the generations of the CPU, the first generation is 4-bit processor, hardly having 16 pins, 1970s. Second generation started with 40-pin ICs, which is a 8-bit processor, 8085 Intel CPU. The third generation is 16-bit processor, 8086, which was popular PC in almost 1980s. Then the fourth generation is after somewhere 84, 85, where a settled version of 80386 DX was released, which is a 32-bit processor, which is having 32 address lines, 32 data lines. It can address up to 4 gigabytes of physical memory and 64 terabytes, that is 2 to the power of 46, 64 terabytes of virtual memory it can address. So that is how, up to fourth generation, it was. Let us try to understand how this X86 is made it compatible to the latest generation CPUs. To begin with, what is X86? X86 is having major changes is separate execution unit, bus interface unit, having set of registers. In bus interface unit, as you can see, it is having segment registers, instruction pointer, instruction queue. The purpose of the bus interface unit is to generate the physical address. Being a 20-bit address bus, it is supposed to generate 20-bit physical address. However, all the CPU registers are 16-bit, but still it should be able to generate 20-bit physical address. So that is the interesting point, that how a 16-bit registers will generate 20-bit physical address. As far as execution unit is concerned, the purpose is arithmetic and logic unit and general purpose registers like AX, BX, CX, DX. All of them are either 8-bit or 16-bit registers. It is also having a pointer registers. You can use it for general purpose or to generate the offset value from stack pointer, base pointer, destination index and source index. So what is interesting here is that these are the offset values and these are the base registers. Combination of these registers will generate the physical address. That's what is the interesting thing of 2 to the power of 20, that is 1 megabytes of real addressing capacity. So even today, even if you say 486 Pentium or the latest generation i3, i5, i7, when you say real mode, whatever is shown in this slide, those registers are called real mode. Real mode means whatever you see in this slide, the registers, the flags, the arithmetic and logic unit, the instruction set, whatever is 8086 provides is real mode. So if you are working in a real mode means it is 8086 mode, where the addressing capacity is 1 MB and all the registers are 16 bit. Alright, how that 20 bit physical address is generated with the help of the 16 bit registers. What you can see is the offset registers, right? These are called offset registers. SI, DI, BP, these are all offset registers. SP. So 16 bit value of offset registers and the base registers, segment registers like CS, DS, SS, ES, they are called segment registers. So segment registers contents will be left shifted. You can see by 4 bits, zeros are added to the rightmost position, is added to the offset value, then 20 bit physical address is generated. What does it mean? It means that the MSB portion of your 20 bit is represented by segment register. Your LSB portion of your 1 MB space is represented by offset registers, these registers. So that is the reason where your number of segments is 2 to the power of 4, right? Because your MSB is 4 bits. So 2 to the power of 4 is 16. You have 2 to the power of 4, 16 segments in 1 MB space. Your entire memory is divided into 16 segments. And what is the size of the segment? It is an offset value, 16 bit, means 2 to the power of 16, that is 64K. So each segment size is decided by your offset value. Since offset value is 16 bit, 64K is your size of the segment. And how many such type of segments are there? Remaining 4 bits. That is 2 to the power of 4, 16 segments. So your 1 MB space is divided into 16 64K segments. That is how your physical address is divided. Alright, so then similarly, if you look at the 386, is a true 32-bit processor, is having 32 address lines, 32 data lines. It is again extension of 80286. 286 is having only 24 address lines, but then it is having 32 data lines. However, 1986 onwards, 386 DX became popular as a workstation, mini workstation. So being a 32-bit physical address lines, the addressing capacity is 2 to the power of 32, 4 gigabytes. So now your physical memory, actual memory is 4 gigabytes. Okay, so it supports 8086 instructions, it supports 286 instructions. That means now it is upgraded. So it's always upward compatible. Every CPU of Intel is upward compatible to the previous generation CPUs. But interestingly, what it also provides is a memory management, protection, multitasking environment. Like I already explained, what do you mean by memory management? Memory management means real mode, virtual mode, protection mode. And also we will discuss some other way of generation of the physical address and protection. And it provides the modes, various modes of addressing called real mode, protected virtual addressing mode, PVAM mode, and V86 mode. When you are in PVAM mode, it also it provides 4 levels of protection we will discuss, and paging is also available in 386. Paging is not there in 286. Page means 4 kilobytes of block. So instead of accessing the complete segment, you can access a small page 4 kilobytes from the memory, secondary memory. In PVAM mode, now interestingly here, your maximum size of the segment is 4 GB. See, why 4 GB? Because your offset value is 32-bit here. So being a 32-bit, your segment size is 4 GB. However, when you are in 286, your offset value is, let's say, 24-bit. So 2 to the power of 24. If it is 8086, your offset value is 16-bit. Naturally, your segment size is 64K. So size of the segment is depends on the offset value. And the 386 is a true sense of 32-bit as compared to 286, which is a 24-bit address space. And like I said, it is capable of having paging mechanism. Whenever you reset the CPU, when you reset your CPU, it is in real mode. Real mode means 8086 mode. If you want to enter into virtual mode, right, protected mode, then you have to set a bit in the flag register, then only it will enter into PVAM mode. It can access 64K, so all these things are anyhow the upgraded version. When you are in protected virtual addressing mode, the number of the addressing capacity goes to 2 to the power of 46, that is 64 terabytes in 386. So now that's the interesting thing, that the physically 32 address lines and virtually 46 address lines. Real means 20 address lines. So real, protected, virtual. These are the three interesting addressing mechanisms of from at least 386 onwards, you can say, which made it which became a standard operations of memory management unit inside the CPU. All right, like I said, though 386 is a 32-bit processor, but if you are in a real mode, you are actually like 8086, like 16-bit registers. However, if you by any chance, if you enter into virtual mode means, for example, if Windows operating system is loaded, Linux operating system is loaded, that means you are enter into virtual mode. There, the real, all these 32-bit registers, 32-bit flags, right? General purpose registers also 32-bit, base registers are 32-bit, offset values are 32-bit, plus you can see some additional registers called GDTR, called Global Descriptor Table. Let us try to understand the protected mode and protected virtual addressing mode from 286 onwards. Like we have discussed, the real is actual, the physical, how many number of pins are there, that much memory a CPU can address. However, x86 mode means the addressing capacity is limited to only 1 MB space. Though you may be using 286 or 386, but real means it is x86 addressing capacity. With the help of the control register, control bit, which is there in the flag register, you can enter into PVAM mode. When there is a bit called protected enable bit, PE bit, in your control register, you can use a instruction called load machine status word, which can load the control register, that is the flag register, to enable the protection mode. Once you are in the protection mode, now it uses the addressing mechanism called virtual addressing mechanism. So virtual addressing mechanism means, as you can see, you have the same segment register act as a selector. The selector selects the descriptor in the memory. Descriptor has the entry. The descriptor table has the entry of descriptor, which consists of the base address. This base address is 24-bit for 286 and 32-bit for 386. So this base address plus the offset value. Offset value means you have offset registers. That offset register contents, which is depends on your CPU. That offset value is added to the base address, then the physical address is generated in order to fetch the operand from a segment. This is how protected virtual addressing mode works, where selector is nothing but segment register provides the base address for the descriptor table, which has a entry descriptor. Descriptor consists of the base address of the segment, and offset value is added to generate the physical address of the segment. All right. What is that a descriptor? A descriptors are two types. It could be code segment descriptor or it could be data segment descriptor, other than the system descriptors. There are descriptors called the interrupt descriptors, or it could be gate descriptors, and so on. So the code and data descriptors, as you can see, is of total 8 bytes. First 2 bytes is the limit. The limit is, as you can see, is 16-bit. That means now it is verifying what is the size of the segment you are fetching. So you can limit the size of the segment up to 64K as far as the 80286 is concerned. And the base address is 0 to 24-bit every descriptor consists of. So before you fetch the segment, the descriptor is providing the 24-bit base address as discussed in the previous diagram. So this base address 24-bit is coming from the descriptor, that is your 3rd byte, 4th byte and the 5th byte. Your 6th byte is the access rights, means this byte, 1 byte, is a attributes for every descriptor, characteristics. Quickly, if you see what is that attribute is, say for example, type and descriptor privilege level and access rights. The last 2 bytes are reserved, but this is used in 386 because there your base address is 32-bit. So what is access rights here? 1 byte access right. Bit by bit is explained here. Say to begin with, for example, present. That means this bit, P bit, whether it's 0 or 1, is indicating the segment which you are accessing is presently available in the physical memory or not. If it is not available, then it has to fetch from the secondary memory storage the address which you are looking for, the segment which you are looking for. Similarly, the 2 bits are called descriptor privilege level. So every descriptor has a privilege level. So since it is 2-bit, you have 2 privileges, right? 0001, 1011. That means 4 combinations of privilege levels, 2-bit privileges. So 4 possibilities. 00 is the highest privilege level, 11 is the lowest privilege level. 4th bit talks about the type of descriptor itself, whether it is a code or data segment descriptor or whether it is a system or a gate descriptor. So right now we are interested in either code or data segment descriptors. Then whether the descriptor is executable code or not, right? Because see, the descriptors is sometimes maybe a system descriptors, so or it could be a data descriptor. So it's an executable version or not, and the other attributes like writable means the descriptor, is it can you modify it, right? Is it executable? Because if it is a code segment descriptor, then it is a executable. And confirmation, C bit is a confirmation. Code segment may only be executed when the current privilege level is greater than or equal to discrete privilege level. That means looking at your privilege level, right? When you are requesting a code segment or a data segment descriptor to be fetched, then what is your current privilege level, and what is your request privilege level, and what is the descriptor privilege level. So now how many privilege levels you have? The code is a current privilege level, and the requesting, whatever you are requesting, is a requester privilege level, and the descriptor which you are fetching, whether it's a code or data, is a descriptor privilege level. So finally, the effective privilege level should be such that it should be greater than or equal to the descriptor's privilege level, DPL. Then only you can access that particular code. That's about the conforming. Then whether it is a readable or not, or that particular descriptor which you have fetched is by any code has accessed or not. Why all these attributes are important? Because see, when you want to replace a descriptor, when you want to write it back a descriptor, do you have the permission to access the descriptor? So these are all one way of saying the protection. One thing we have seen is that the limit. Limit means, are you crossing the limit provided by the descriptor or not whenever you are fetching a segment. Second, the attributes. The attributes are saying your access rights. Are you allowed to access? Are you allowed to write? Are you allowed to execute? Is the segment is present? And so on. What is the third way of protection? The privilege levels itself. The code from which you are executing, that is about your current privilege level, and you are requesting, right? When you are requesting, that is selector. So the selector also has a privilege level. So this privilege level and the descriptor as a privilege level, DPL, this privilege level. So requester's privilege level, right? That is a current privilege level should be always greater than or equal to the descriptor's privilege level. Then only you are allowed to access a segment, whether it is a code or data segment. So these are the kind of protection is available from 286 onwards. So we have discussed about what is a real mode, what is protected mode, what is virtual mode, what is in 386, what is x86 mode, right? So these are all the memory management features which they started implementing from 286 onwards till date. So when it comes to selector, what is selector? Selector is nothing but your segment register, which is a 16-bit. But in this 16-bit segment register, the upper 13 bits are acting as an index value. Means they are selecting the table. Your descriptor table is coming because of your selector's upper 13 bit. So upper 13 bit means what? Upper 13 bit will give you 2 to the power of 13, right? 8K descriptor tables, right? You can select those many entries. But however, the TI bit, here you have a TI bit which indicates whether it is a global descriptor table or a local descriptor table. Now what does it mean? That means that the descriptor itself can be two types. It could be a global, it could be a local. So that means 8K, because 2 to the power of 13, 8K I can have global descriptors, 8K I can have local descriptors. So that means 2 to the power of 13 plus 1, 2 to the power of 14. So 2 to the power of 14 plus in 386 it is 2 to the power of 32, because there you have a this base address is 32 bit. So offset value, right, plus this base address is giving you 2 to the power of 32 plus 2 to the power of 14, you are getting 2 to the power of 46. That's how this 64 terabytes of virtuality is coming into picture. So requested privilege level, again every selector is selecting the descriptor table. So the requester privilege level, again you have 2 bits. So requested privilege level, current privilege level, descriptor privilege level is what is called effective privilege level, should be greater than the descriptor privilege level, then only you are allowed to access a specific memory location. Alright, so what is the difference between a global descriptor and a local descriptor? If it is a global descriptor, that means a global descriptor means global descriptor can be accessed by any task, right? Any task can access the global descriptor. But if it is a local descriptor, then it is specific to a specific task. That means every task cannot access this descriptor. So that is how they are differentiated. Even within the memory also, you have 2 types of descriptor tables. One is global descriptor table, second is the local descriptor table. Alright, now finally what do you mean by privilege levels? You have privilege levels 00, 01, 10, 11. 11 is the lowest privilege level. Generally application programs uses the lowest privilege level. Otherwise the 00 is the highest privilege level, where the operating system uses the highest privilege level. So now, as we have discussed, it is all about the comparison, that what is the current privilege level. From there you are accessing the descriptors, right? It could be global, it could be local, it could be code segment, it could be data segment, but finally the current privilege level should be greater than or equal to the descriptor privilege level, then only you are allowed to access. So these are the ways of implementing the protection in the x86 based CPUs like 286, 386, 486. Now today we have i3, i5, i7 and so on. Similarly, we have discussed about what is 8086, what is real mode, what is virtual mode, what do you mean by protected virtual addressing mode. Alright, so that's all about the PVAM mode of these Intel based CPUs. Now next session we will discuss about what is the operating system which was used in 1970s till 1990s, and then today also we would like to use the same operating system called DOS. Then only if you are using the latest computer, but still if you want to execute your program in real mode means x86 mode in latest generation computers. So when you are in real mode means the addressing capacity is only 1 MB space. Though you may be having 64-bit registers, though maybe it can address terabytes of memory, however, it will limit to only 1 MB and it will limit only to 16-bit, 8-bit or 16-bit registers. So that is possible only if your computer is loaded with the DOS operating system. So this we will discuss in the next lecture.